Hello everyone, I'm Mohammed Waqas Arshad with my team member Professor Stefano Lodi from Department of Computer Science and Engineering, University of Bologna. We would like to thank our organizers to give a chance to present our work on optimization of double wishbone suspension, evaluating the performance of classes of algorithm. This work is partially supported by Ferrari and PNR. So let's start towards introduction. So today I am discussing the vital role of suspension systems in vehicle. Suspension is crucial for enhancing vehicle dynamics, ensuring stability and improving passenger comfort level. So these systems are the fundamental component that connect the vehicle to its wheel and help among the road shocks and handling the forces. And one of the most effective type of suspension that is a double wishbone suspension, which offer a preferred performance vehicle due to its ability to offer a precise control of its our wheel motion and the camber angle. So you can also see in this diagram, this is how it's look like about double wishbone suspension. This is the wheel and within upper arm and lower arm. So it's also called as an A arm suspension system. So that basically separate the shock and the spring load, allow the better camber control, and which is a critical factor in vehicle stability and cornering. So by maintaining this optimal geometric alignment, it provides superior handling characteristics that are essential in sports car and high performance. Even this double wishbone suspension is basically used in Formula One car. So here below about the camber angle. So camber angle is basically the angle at the wheel and the tire stand relative to the road, assuring it's perfectly flat. So the ideal camber angle that basically help to optimize the road contact and like wheel is crucial for effective handling and minimizing the tire wear that improve stability and increase the longevity and more dynamic driving experience. So here there's a different type of camber, negative camber, neutral camber, and positive camber. Every camber has its own need and have own pros and cons. So let's go to our problem statement. So this is about the first about our design challenge, like the multi-objective problem. So, like designing suspension is a complex task which include a multi-objective, various quantities. If we discuss like a camber, toe, so it's very difficult to balance these quantities and that vary during wheel motion and very complex to design this process. So, like our goal of designing that is also really complex task about minimizing the deviation from desired performance, but have also be considered the mechanical constraints, and then further have to do the optimization in a term of computationally, like in a less time to decrease the development cycle and get less computational power to enhance the design process. So that is what our problem statement. Let's go to our objective. So the first what we have to do is to drive the model of for the camber angle that including some geometrical parameters, and then we'll do the comparison of the performance of different optimization algorithm which we're going to be perform and compare their result, and then do the optimization goal. That is one of our main goal, to minimize the camber angle deviation with the specific constraints along the algorithms which we use, because we're using a comparative study of algorithms, different type of algorithms. So we apply all algorithms and based on objective values, computational and time, and memory usage. So that is our goal. So this is like the recent related work on double wishbone suspension, like how different researchers do what type of optimization technique and what are their finding. Let's do a quick overview, like design optimization, improve camber caster control in motorcycles, and then static stress analysis, basically safe fuel under high speed and stress. Then weight optimization is also significant weight reduction for armored vehicles, and use the genetic algorithm, accurate prediction of wheel alignment, and nonlinear dynamic, finite element analysis, so particle sum optimization. So let's discuss about our methodology. At the first, we will create a 2D model, a geometrical model using some trigonometry for the camber angle and overall try to did the design of double wishbone suspension, and then we'll apply a different multimodal optimization approach. We'll discuss in next slide on applied to the camber angle, and do the comparison of different algorithm classes, and then identify the best optimal suspension parameters for the desired camber characteristics on the basis of these optimization algorithms, and evaluate each algorithm effectiveness. So here let's start with the suspension geometry and the camber angle deviation. So this is the geometrical diagram of our double wishbone suspension. So these are the components with the lower arm pivot O1 here, uh, with the 0 0 origin, and then we have an upper arm, see this one at O2, and these are the lengths, L1 here, L2, L3, so H knuckle, and here gamma is our camber angle. So these are the different angle which we make during this geometry, that will be help to find our gamma. So we need these, and here next we will also drive about the camber angle equation in the next slide. So here is all the equation. So first we start with calculating the distance between the point P1 and O2, so which is basically the U. Using this equation we found U square. So this is L cos theta, and 1 sine 1, yeah, L1 sine theta, L1 cos theta. So we are do this geometry stuff. Here this is open the formula, like m is p square, and this is like more extracting the depth, L1 square cos square theta and plus z square, and open this formula, and we get this equation. Make this equation number 1, and then apply the law of cosine to the triangle P1, P2 and O2. So here it forms. So from here we get this alpha, and with the cos theta of L2, here is it minus U2, which we get from here, minus L3 over 2 L2U. And then we calculate the beta angle between P1 and O2, which is this one. So we get this equation, and the next we calculate the camber angle. So which is basically the difference between the equation 2 and equation 3 with alpha and the beta, and which is then we substitute equation 2 and 3, and here we get alpha, this one, and minus beta, this one. And after that we place the value of u square, this one here, and then this is our gamma, like for the camber angle. So this is how we basically derive the camber angle. So next about the constraints and the objective function, like I already discussed, by focusing on the camber, we also have to focus on the constraints. These are also part of our objective function, like parameters which we have in the geometry edge L1, L2, L3 have some minimum and the maximum particle bound, and then we have slack constraints, upper and the lower slack constraint, that will ensure the mechanical feasibility and introduce flexibility while maintaining a system constraint. So here's an upper slack um, with the sign theta min greater than equal to this equation, and same for the low slack, it's opposite to this. The max of sine theta is less than equal to this form. Then the objective function is basically to minimize the deviation of camber angle as a function of theta from the midpoint between a lower bound and the upper bound theta, that delimit an acceptance region across the range of theta values, which also shown in the next slide, the visualization that will be easy to understandable. So here's the aggregation of objective function over elevation angle kappa. So this is theta high, the maximum above one with this objective function, camber angle with these all the values, minus low one. So like it must be fall between uh, this range, the camber angle. So then the minimization problem, have to minimize the main camber angle, the set of elevation. Kappa will be chosen as evenly spaced set between mean and max operation angles, and the lower bound and the upper bound height theta will be defined as a linear function of theta and interesting camber angle, sorry, intersecting at a camber angle, the specified elevation. So next, these are the optimization algorithms which we apply in this project, have categorized into four main types: deterministic algorithms, stochastic, materialistic, and direct search methods. These are all good for optimization problem. So here we have interior point method, gradient descent, random search, simulated annealing, genetic particle swarm, and ultimate method. So yes, so about the optimization methods, all the optimization method which we apply, we uh, run with the 50 iterations with each, and with the population size of 1000 parameter to for the balance exploration and exploitation, basically for these methods materialistic algorithm, genetic algorithm, particle optimization. So have the fixed 1000 iteration for this, and for other we have 50 mean iteration. So the evaluation criteria which we focus on the memory usage because already discussed about the number of iteration and the computational time as our goal, uh, and the main is objective value minimization because like computational power it's also one of our problem and goal which we have to focus on because less computational power it take and it give the efficient design problem it will be helpful. So these are the result and analysis. So here we get the better result with the interior point method because with the low objective value and average time and the memory consumption, here's the table. So here's the visualization. It shows all the visualization for different methods. Simulated annealing, it's a bad one. Did not give the good result, but other it's in the region which already discussed earlier. But on the basis of this computational power, objective value, average time, memory, so the interior point give the better one because it's a deterministic method outperform meteoristic and stochastic method in this constant and this is best served with the complex constraints. So for our case interior point method gives the good result and this is a simulation on the runtime get the optimal values and if we change these values it will be must be in this region. So this is like some sort of try to make a double wishbone suspension. These are so the conclusion is basically we develop and optimize double wishbone suspension geometry and the interior point method is identified to be the best among the other algorithm and we also check out the importance of algorithm that not like all these particle sum optimization methods always good for every problem. So this case like interior point method is good for convince problem and give the better result. So we provide the comparative analysis of various optimization algorithm and which demonstrate the significance of constraints handling and optimization in the future. We will try to work on 3D suspension model and already in process and also other mathematical approaches that is also already in process which are doing and yes there's another approach we can also do the integration with the real world testing validation that is also we can work on future. These are the references. Thank you. Thank you.